Pete, thanks so much for the kind introduction. Welcome, everyone. Really exciting to see so many people here today. And I have the pleasure to give the introduction to generative AI today. I guess I've only an hour left, so I will skip some slides, but I hope I can provide you a little bit of an overview and talk about some of the principles to set kind of the stage for the coming talks. I want to briefly say the agenda is online. You're probably all aware of that. Join the Slack channel so we can have discussions there if you have some questions which we can't answer during the lecture or in the breaks. Just ask a question there and we can follow up. And use like the breaks to network. Don't be shy. Talk to the lecturers. We have like a great program. We cover really a broad range of topics this week. So use the opportunity. Well, I don't need to reintroduce the org team, but I want to thank again like the admin team. This would have been possible without Mo and Celeste, who you have probably interacted with, who did like an amazing job. So please thank them again. Okay, so this is my agenda for this talk. I want to give a little bit of motivation about why generative models are exciting for science. So who has used a generative model? Probably everyone, I guess, GPT. Okay, perfect. But who has trained a generative model? So, okay, it's quite a lot. So I don't know if I tell you anything new today in this lecture, at least. That will be all very basic, but I hope we will all have the same pickup point after this talk. So yeah, I will talk a little bit about the foundations of probabilistic modeling, and then in this lecture, I want to briefly cover variational autoencoders. We have like a tutorial session later today as well, and you can decide if you want to work a bit on variational autoencoders or later on train a diffusion model. I don't know if I will talk much about the landscape of the generative models, but give a brief overview, and then all these models will be covered in detail later this week. Okay, so probably don't need to motivate generative AI much, but like since the event of ChatGPT, we're all using it now. It's great for text generation, for code generation, and typically you kind of provide a prompt, right? And it creates a response based on that. So you do some conditional generation. What is really amazing are kind of generative models for image-like data. And what I just want to show here, what is interesting about these models is they can like, I give an instruction here, a teddy bear on a skateboard on the moon. So these are kind of different concepts, and the model is able to put this together, right? So it knows what is a teddy bear, it knows what a skateboard is, it knows what a moon is, and kind of the skateboard is on the moon. So it kind of learns to understand these concepts, and it has to in order to put it together and generate something that is meaningful. Maybe the physics are not perfect if you look to the reflection in detail, so these models have like some flaws, but I think still this is pretty impressive what they can do. And then you have like video generation models. So this is like a generated video. If I look to it, like the first time, I couldn't really tell if that is like a real video or if this is generated. So basically what I truly believe, and I think that's also a bit the vision of OpenAI with the Sora model, is that generative models can eventually be used as a world simulator. So if they can be used as a world simulator, we can certainly use them also to simulate scientific phenomena. But there's a long way to go. So it works very well with natural images or natural videos, but these models are not really able to accurately model the physics of many basic interactions. For instance, they have like a nice video about trying to a glass falling on a table, right? And the model wouldn't get the glass shattering correct. And that will probably, I think, take another 10, 15 years before these models get the physics really, really right. So there's a lot of research that can be done. So this is an exciting area. And I think if you're looking for a research direction, I think this is like an interesting area to work on. So I believe, as I said, like these models will also drive science. I mean, why do we need AI for science to begin with? We can ask that, right? We kind of, if you're a scientist, you typically use some mathematical models. You use PDEs that you derive from first principles to describe complex phenomena you like to study. But PDEs can be challenging, particularly if you don't know the exact physics, the underlying physics. Think about earthquakes. You maybe don't know the exact topology of the ground. So it's really hard to derive a very good model to capture everything, to kind of use this model for predictions that are meaningful in practice. So deep learning, or specifically Gen AI, kind of allows us to learn from data, and we collect more and more data anywhere, right? We have satellite imagery, the resolution of these data become better and better. We have sensor stations across the world who measure all kind of phenomena. So we can use these data that are typically very high dimensional and use a deep learning model, a generative model, to learn from these data. The advantage is, like, I mean, that might be an advantage or disadvantage. We don't need any explicit knowledge. We basically can just learn from the knowledge. And if you kind of, or some people at least believe, if you give me enough data, then the model should learn the physics from the data. The problem is, in some cases, we might not have enough data to learn the physics. But then there are also hybrid models, is that if you have some knowledge, you maybe can inject some knowledge into these models. And another advantage is maybe these generative models are expensive to train. I mean, you will get a bit of feeling later in the tutorial. They're actually expensive to train, but they are relatively fast during inference time, typically faster than a traditional physics-based simulator. So there are some advantages. I'm not saying generative models will replace traditional methods completely, but at least they will help us to augment those. And in many cases, they will help us to accelerate scientific discovery. So some problems I'm interested in, and we will hear a little bit more about those problems, I think, on Friday. I think Arash will talk about these problems a little bit as well. So one problem is like the super resolution problem. Basically, you're given with some coarse-grained data or low resolution data that might come from a satellite, and you want to use a model to extract fine-scale data from it. So basically, again, you can formulate this as a conditional generation problem, generates a high-resolution snapshot given the low-resolution snapshot. And generative models do extremely well for these type of problems. And we're kind of in the tutorial this afternoon, we'll focus on this little region there and try to build a diffusion model for generating this output here. And another problem related is, like, maybe you just don't want to super resolve, but maybe you want to forecast spatial temporal data. So this becomes also like a relatively challenging problem depending on the resolution of your data. But again, like diffusion models provide a very interesting approach to forecasting. So typically a challenge, I think, that we have currently is these generative models quite often make a strong Markov assumption that basically predicts the next step just on the previous step. So that's relatively limiting. We can use also an autoregressive approach, but this becomes very expensive to train if your data are very high dimensional. So kind of balancing or find something in the middle, I think, is ongoing work. So here are some challenges that I think we encounter when dealing with these data. So in these data, compared to if you work with natural data, like you have an image, right? You have an image and you might have three channels, red, green, blue, and these channels are highly correlated. But if you work, for instance, with climate data or maybe fluid flows, you have like different variables. These variables might be maybe not completely independent, but maybe weakly correlated. And they can have very different scales and different physical units. So kind of modeling them jointly is like quite a challenging problem. Another thing is that maybe these relationships between different variables are highly nonlinear, and they might overlap in some regions, but maybe not in the other regions. And the dynamics are typically time varying. So this is kind of an interesting test bed for testing these models. I mean, I'm personally not interested necessarily in the problem itself, but I think these problems are interesting to test, to stress test generative models and see what they can do and see where they fail and ask the question how we can improve these models further. So what I want to say here as well, it depends a bit on your problem, what you say, what is a good model or a bad model. If you look to model 1, 2, and 3 just by visual inspection, I don't know if anyone can see a difference. So I can hardly notice a difference. So kind of, if you just want to generate something and look at it, typically how you do it with natural images, then it doesn't matter too much if you get like the high frequency features right. But the high frequency features might be relevant if you want to use these data for some downstream application in science, where a scientist maybe cares not so much about the low frequency features, but about some high frequency features which capture some important physics. And there's a real challenge in these models that you see, like I show on the right, just basically these different models, and you see some models capture better the high frequency features and some not. Like model 1, in this case, I mean, it's a simple problem here. Model 1 captures the high frequency features very well, whereas model 3 and 2 is not capturing them so well. But by visual inspection, you wouldn't know. And in general, a question is how can we force these models to better focus on high frequency features, which matters for scientific problems. So here are some more use cases. I don't want to talk about them in too much details, but I think we will hear about some of these use cases this week. There is like generative models are really great for protein generation. I think Arash might talk a little bit about this. We will probably hear about material discovery on Friday by Taylor. Daniela will talk about time series forecasting, using LLMs for time series forecasting. Another application, I think we don't hear anything about it, but like we can use generative models for simulating ground motions from earthquakes. And then, of course, I have touched base already on weather forecasting problems. So if you have questions about these use cases, just come stop by and we can chat more about them. Okay, perfect. Let me talk a bit about some foundations, just that we set up a pickup point for this week. So first, let me kind of briefly revisit discriminative models just in a nutshell. You all are familiar with regression problems and classification problem, otherwise you wouldn't be here. So it was like part of the selection problem that you have experience with these models. And simply we have discriminative models. You can think about it learns a map to map an input to an output. So classification is like a good example where we're given an input and we try to maybe predict the probability of the class label. And here I use a puppy. Sometimes like using cats and dogs is visually more appealing than using scientific data. So nothing special here. So if you talk about classification, then typically what the model is doing, it's just learning a decision boundary. It just tries to learn how to discriminate between maybe two classes in your data set. And basically, it learns some features to make the classification, but those features might be not meaningful at all. So that's an issue, right? So there is like, for instance, here, if you try to classify between a dog and birds, then you might see that the dog is typically, you have a photo, an image where the dog is playing in the garden. So there's a green background and birds are typically flying, so the background is blue. So the model just maybe learns to discriminate the background and not learning actually features that are meaningful describing what is a dog, what is a bird. These models essentially learn a conditional distribution, and they do not learn to understand the underlying process. So that can be very useful in many situations, so there's nothing wrong about it. But a generative model goes a step further, and it tries to learn something about the underlying process. Of course, this is much harder, these models are harder to train, but if you have a good generative models, then you can do more with them. Okay, I said like generative model tries to learn the underlying distribution that generates the data. So you can think about the data distribution, if you like, about something very abstract. And this might be physically meaningful, or it might be just a mental model. Quite often we think about it as form of as a density. And you can think a bit about the data distribution assigns like maybe a likelihood to the outcomes and tells you whether an outcome is more likely than another one. Okay. The only thing we have access to typically are data. We don't have access, we don't know the true data distribution. So what a probabilistic model is trying to do is it tries to learn a model that provides a good approximation for the data distribution. And if we can find such a model, then we can essentially do 2 or 3 things, depending on how you see it. So first of all, we can do density estimation. If we have a model, or if we have like an approximate density function, then we can basically ask how likely is a certain new data point under this model. So here, for instance, if we have a model which just has basically models like cats, then if we show another image of a cat, it should be likely under this model, whereas a bird would be an outlier. It should get assigned a low probability. The second thing we can do is, we're often interested in sample new data. Quite often in science, we're interested in simulating. We want to simulate new data, and we can use a generator as a simulator, if you like. So, and we hope that kind of these new data are somewhat realistic, and as better we approximate the true data distribution as better, then again, like what I discussed before, the question is, are the physics correct or not? So that's a big question. So in summary, we want to generate data or measure how likely a data point is, or learn representation. So in modern generative models are typically mainly focus on generating data. Not every generative model can basically provide you with an estimate how likely a data point is. Okay, just as a recap, density estimation. As I looked at some old lecture notes. So I studied stats, and density estimation was a topic. I thought this is like super boring because like if you look to this, you saw like, okay, looked at histograms and stuff like why do I want to fit like a Gaussian distribution? I never really thought about from the perspective, okay, I can generate new data with that. But like looking back at this, I think like it's actually interesting looking at some of these basic intros to density estimation to get a feeling. So it's a very classical approach studied for many decades. And essentially, we want to kind of learn an approximation for the density function. And if we have this, we can ask how likely is a particular data point under the model. So kind of you all have kind of done this, whether you knew about it or not, because I think everyone probably has created a histogram at some point. And that's essentially just an estimate for a density function. And if we have this density function, we can then ask, for instance, about a range of data points, how plausible it is to observe maybe a data point in a certain given range. But so this is like a simple problem. So this works very nice in 1D, maybe in 2D. But this becomes a really hard problem once you go to higher dimensions, right? So don't try to do this with an image, which maybe has a million of dimensions. So it might be very limited, the use case. Useful to get an understanding, but limited in practice if you deal with high dimensional data. So generative modeling here, as I view it, it's more like, it's not about necessarily learning the density. It may or may not learn the density. So it's not necessarily about asking how likely is a data point. It's more about sampling new data. So you can see this as a sampler, as a simulator. Basically, you can think about it as this two-stage process. We draw a sample from some base distribution, and you define the base distribution. Basically, you choose a base distribution that is easy to sample from. Like a Gaussian distribution, you could probably use a uniform distribution, so something that is easy to sample from. And then you learn like a map, a model that transforms basically the sample to a data point that mimics the data of interest. So what you should realize here is the second step, our G is deterministic. If I have the same sample from the base distribution and I send it through G, I get always the same answer, right? So the randomness only comes from sampling from the base distribution. So we should keep that in mind. You can formalize this maybe by viewing this through the push forward measure, but I think this is like a good mental picture, very simple. And you can kind of here, like if you prefer like a visualization, again, I draw here like some realization from a normal distribution. I send it through my network that I have learned, and I get some observation X here. Okay, so learning this kind of G is like not that easy. There are many ways to do that. And I guess that's the topic of this week. What I want to mention is like, I think for most problems in the example I gave at the beginning is that we typically have a conditional generation problem. So I typically don't care about generating an arbitrary sample from my distribution. I want to condition it. And that's like typically what you want to do if you do some simulation, right? I mean, if you simulate it, you have some parameters that you set, and then based condition on these parameters, you want a simulation. For instance, with climate, you could say, okay, I care about here, this is like a kinetic energy. I want to learn what is a plausible field in July. And not have it like maybe July and even the year, maybe July 24. So you can condition it under certain variables, and you have to define those, and depending on how you define it, you have to train a new model. And again, it's not changing the base distribution. Still, we just sample from the base distribution. The only thing which is changing our model G is now taking an additional input so that we can condition it under some auxiliary information of interest. Okay. And it's like always relatively simple to go from a generative model to a conditional generative model. Essentially, your network just takes some additional input. So there it's not a big challenge here. Okay. So if you have generative modeling, I think that's really interesting because then you can do predictive uncertainty estimation. So basically here what I do is I draw many latent variables from my base distribution, and then I send them all through my model G and create conditional outputs for some conditions C. So I get like an ensemble of samples, and then I can just average them to get a mean prediction. And I can compute like the element-wise variation or standard deviation. And here's a map, and you see like where are some uncertainties. And you see like these uncertainties look a little bit artificial here. So this kind of results, like you see like basically a grid that we learn this model on patches, not on the full image. And you have like these boundary artifacts. A model is good like in the center, but like on the boundaries, it doesn't have the right information. Okay, so this is an example you will see later in the tutorial. Okay, let's see. I thought like it's good to have a look to a simple toy example just to go through it. Not very exciting, and it's like artificial and made up. But basically, assume like you have like a like some sensor measurements. I have two sensors here, and they're correlated, so they're kind of related to the same scientific experiment, whatever experiment that is. And here in this case, like quite often you maybe start with plotting your data, looking at your data, and then one approach is you look, okay, at the shape of the data, and you may or may not see that there is some Gaussian pattern. But let's assume we believe there's a Gaussian pattern. So then we can use this as one approach for this problem and use a very simple parametric approach to model these data. So for density estimation here, in this case, if I use a parametric approach, I basically just start with a probability density function of a Gaussian distribution. So this is like some exponential function that is like normalized so that it integrates to 1. And like the task here for density estimation is to learn the parameters mu and sigma. So this is a very simple problem. You probably have done something like this before. You can just use maximum likelihood to do so. But like once you have these parameters for our data here, what I said before, we can now evaluate how likely a new observation is, right? I have my density function. I have an estimate for mu and sigma, and I can just plug in now a data point. So typically, we take the log of the density, the log density, just because it's nicer to work with the log. And typically, we define the score as the negative of the log. And so I have 2 points here, like this blue star at -3.3, and I plug it in, and I get like a score of 15. So that's a relatively large score. So basically, this tells us, okay, this data point under our model is a rare data point or maybe an outlier. And then I can check another data point, 2.2. It has a small score, so this is a plausible data point, right? So this is like what you can do if you estimate the density, you can answer these type of questions. And you might want to use it for anomaly detection just to understand your data better. So very, very simple. And now this model doesn't allow us, so if I have the density, the question is like, how do I sample from it? So you probably have all sampled from a normal distribution before, but just to see this two-stage approach, I will kind of use this example to sample new data. So I define a base distribution. The base let's assume you open PyTorch. You might know how to type numpy random standard normal. So it's very easy to sample from a normal distribution, right? And I want to learn a map that takes me from a sample from the normal distribution to the desired data distribution. So what is this G? That's very simple for this problem. If I have a Gaussian, it's basically just a linear function where I have two parameters, A and B. So B here is just the mean. I shift my data with the mean, and A comes from the covariance matrix. Basically, you compute, you factorize the covariance matrix, use Cholesky decomposition or whatever. And basically, then you multiply your random variable or your realization by A at the mean, and then you kind of get a data point that resembles the true data distribution. Okay, so that's very easy in this simple case. But of course, you believe, I guess, that the simple distribution doesn't necessarily, a simple Gaussian distribution helps us to model more complex data. So in fact, if you go back to our example of this unknown data distribution of our cats, even if I use a neural network to estimate maybe the PDF of a Gaussian, it might be very hard to model this complicated data distribution. So we need some heavier machinery to learn a model that allows us to sample from a complex data distribution. Okay. So why not just using a deep neural network and learn like some function f? So that seems like a good starting point, and we basically could use this exponential function, which is general. But the problem is, like, if you want to learn a PDF, right? I mean, we have like two constraints. The PDF needs to be positive, or the outcome needs to be positive, and the PDF needs to integrate to 1. So we need a normalization constant. And learning kind of this normalization constant Z is like typically a hard problem that makes the whole problem intractable. So many different generative models come up with different ways to bypass this issue. And we will look to one example in a second, variational autoencoders, which allow us to bypass this issue of learning this intractable normalization constant. I just have it in here. I will not dwell on this. You can go back to the slides, but just as a refresher. So what you should know is, like, of course, what is an expectation operator? I think that should be very clear, and go between the integral formulation and the operator formulation. You should be familiar with the factorization rule, which comes in handy, and we will use it a few times in the following slides. Base rule should be probably pretty basic. Have an idea what the posterior is, the likelihood, the prior, and then we have, you see different names. We might think about PX as the evidence, or the marginal likelihood, or the marginal distribution. So it's a handy tool. And then you should be familiar with how to compute a marginal distribution by basically just integrating out the latent, or like the Z variable, the latent variable, which we will call it in the following slides, to get your distribution P of X. So if you're not familiar with that, ask ChatGPT, it will explain all these concepts in great detail. I also don't want to dwell too much on the KL divergence, but also just the concept. You can, I mean, it has some nice information theoretic interpretation. Again, it kind of essentially for us, we try to measure the distance between two distributions. Q is typically the distribution that we try to learn or approximate, and P is the reference distribution that we believe is true. And think about it as a distance, but you can read up on it. I mean, it's like actually really fun to dive into it and read a bit about it from an information theoretic point, if you like. But yeah, so we just use basically the definition that I have on the slide for the derivation of the variational lower bound. Okay, great. Okay, I think I have a half an hour. Let's see if I can go through it. So I don't know who is familiar with variational autoencoders in detail. Okay, quite a few. Okay, so you can lean back. I don't know if I tell you anything new. There will be a bunch of equations that I show. I think yeah, I don't know. It's fun to look at them, but you might have seen them. First, we should start with like, what is a latent variable model? So this is a modeling assumption now, right? So what I said before, like we can't directly learn typically the distribution. We're interested, so we need to make some modeling assumption. So one assumption or one paradigm we can say, okay, that the problem of interest might be described by some latent hidden factors. Whether they exist or not is a different question. Let's just believe it. Like if your data are compressible, then typically there are some latent factors. Are they physically meaningful? Often they are not, but that's fine. But you can find a compressed representation. This compressed representation can be thought of some latent factors, which we obviously don't know, but we can try to learn them. So if that is true, what we can do is then, instead of modeling like P of X, we're modeling the joint distribution Px of and y, right? And we can factorize that. So that's just a starting point we can use. We use some factorization. Typically, you always use some form of factorization to make the problem handy. Okay, so let's say we have access to P as to the likelihood, like to the conditional likelihood X given Z, and a prior distribution P of Z. Then we have like a very simple approach for our generative process, right? Again, like I draw a sample from the prior distribution, and then I use this conditional decoder to generate a sample of interest. Okay, so the question is, how do we, you see like this P, the conditional decoder has some parameters that are unknown, and we have to learn these parameters. Okay, so probably the most standard approach to learn some parameters, if you like, is you have data, you want to learn a parameter, you use the maximum likelihood method, right? That's the standard starting point. So basically, we are asking, given a data set, we try to use this method to find CEDAR that maximizes the log likelihood of the observed data. I formulate everything in terms of the log just because it's nicer at standard. Okay, so now suddenly here in this problem we have P CEDAR of X. Okay, so how do we get P CEDAR of X? Essentially, we can just we can think about it as a marginal distribution here. So we have to compute this integral. So over P CEDAR of the conditional distribution X given Z, and the prior distribution that describes our latent variables. So the problem is this integral might be very hard to compute if our latent variables live in a high dimensional space. If our latent variables might be might be discrete, like maybe binary variable. So this would be probably a tractable problem. But if that comes from some high dimensional distribution, then good luck to try to do the integration. And similar, depending on how we parameterize our conditional distribution, this might make the problem relatively hard. So you could say, okay, I use Monte Carlo simulation, so that would be an approach to tackle this problem, but that's typically computationally relatively expensive. Okay, so this is kind of a roadblock. We're going back to the slide. I'm just down like the things I have on the slide, which I showed before with like these basic concepts. So we have like 5 concepts we used already, I think 2. So Bayes is another approach we can try. Basically, Bayes introduces here like a posterior distribution. And then if you have a posterior distribution, we can rearrange this and get a different approach or different formula for computing P theta x. But again, this problem is, of course, also not tractable for the same reasons we discussed on the previous slide. So why do I show this at all? Well, what is nice, or what there is, like, maybe I don't need to compute the exact posterior distribution, but maybe I can get away if I use an approximate posterior distribution that is simple to sample from. So it's again a model assumptions. Anyways, I mean, all models are wrong, right? So we often simplify it. The question, is it useful at the end? And variational inference provides us with a path forward to learn an approximate posterior distribution. Okay. So again, what's the problem here? We want to, we have like our Bayes rule. We cannot use compute directly the posterior because we can't evaluate our P theta. So what we try to do is, can we learn an approximation that is maybe a good approximation for the posterior distribution. And this distribution, again, should be somehow simple. We denote it by Q, and it's parameterized by phi. So just a different set of parameters. Okay. I'm saying this, we will see this before, like, again, we use a Gaussian. Gaussians are nice, they're simple. We know how to handle with them. So I might assume Q is just a simple diagonal Gaussian distribution. And I hope it provides a good approximation for this unknown posterior distribution. And if you can learn this, then we have like a path forward. Okay. So let's see how this is useful for doing something. So there are different ways how you can start to derive a VRE. I'm just using one, which I like. Again, we want to learn, I mean, in the best case, we want to know the density function P theta. So we can't compute it. But what I can do is I can just multiply it by 1, right? Okay. And here I take like the integral over our proposal distribution. It's a density, it has to integrate to 1, right? So I just multiply this by 1. That's totally valid. So everything here is like, I don't know, it depends what's the background. I think for me, it's always like a little bit magic. So you multiply things by 1, and then things suddenly work out. So we have twice, we do twice magic here in the derivation, multiplying something by 1. Okay, so that's valid. So now what I can do is I push basically the log density or into the integral, and I replace, we use Bayes rules and basically just substitute. right? So now I've kind of this new relationship here. And well, so far that is not too helpful. But again, what I can do now, I introduce another term. Basically, I introduce again the ratio of our proposal distribution and multiply this in here. And now I can do some rearrangement of this term. So let's see what happens. So to do a little bit of work, I can split the terms and I have like now two integrals here. And if you look at this, and basically we can go back to our slide deck where I had like these 5 key properties or concepts. On the left, you see it looks something like an expectation. On the right, it looks something like a Kullback-Leibniz divergence. So we have done some magic to get like these two terms. And essentially, we getting to this result here, and we call the left like the evidence lower bound, and should be clear in a second. And then on the right, we have like this KL divergence. So that's not really useful, right? Because I can't really evaluate the KL divergence because I don't know the true posterior. So this is like also called the inference gap. We forget about this term. So the Kullback-Leibniz is always positive, right? Or non-negative. So basically, the elbow provides a lower bound for the evidence. That's also the name of the term on the left side. And the elbow is nice. I can work with that. Okay, good. Again, this elbow here, the derivation is not yet useful. So we have to do a little bit more work to do that, but it's relatively easy. I just use the factorization rule to replace like the joint distribution. And then what I can do again is doing some rearrangement and split this into two terms. And this looks pretty handy now. So suddenly I got rid of the joint distribution and suddenly I have like some prior here. So it's a bit magic again. And there we will see, I will show you some examples. There are some issues with that, right? Because we try now this proposal distribution Q, we try to, which is a conditional distribution, and we try to match the prior. But of course, it should not be exactly the prior, which I show in a second why that is. For me, I mean, this is why I'm not a big fan of variational autoencoders, and I think they're a little bit tricky in practice, but this is like an approach to do something that we can compute. And on the left, you have basically this term just measures the reconstruction quality of your problem. So that's basically just a conditional. You can think about it as a decoder. Okay. So how do you connect this now to a variational encoder? We have like now this evidence lower bound. So let's make this useful. We have like this formulation here. And if you think about these different terms, you may or may not see some resemblance to an autoencoder. So given the conditional distribution of X given zeta can be just seen as a decoder. Gets something from the latent space and I try to decode it. Our Q can be seen as an encoder. I have a data point and try to encode it in some latent space. And P is just some prior distribution that we choose. In our case, like a normal distribution. So I can just use a neural network or an autoencoder to parameterize these different terms. And if you like, you can think about this in terms of a visualization. We have a data point, The encoder maps it to a latent space. I dive into this in a second. We set like our proposal distribution as a Gaussian. So we learn a mean and a variance term. And then I can sample from the approximate posterior to get a latent variable, and then I map the latent variable through my decoder to get a generated sample. Okay. Let's have a look to the encoder quickly. Again, we have like here our approximate posterior. We parameterize it as a normal distribution. We need to learn the mean and the variance. So these are parameterized by our encoder. So here's like a quick snippet. So it's like super easy. It's like a few lines of code if you have something very simple. Basically, we have a fully connected layer that takes like our input X, X, our data point as an input. And then we have some hidden representation Q, and then I feed Q to two different linear layers, one to learn the mean and one to learn the log variance. Why do we use the log variance here? This might come out of the blue, but think like the variance or should be positive, right? But a neural, like a linear layer learns like basically real values. So the values can be negative. So a simple trick is to learn the log variance, and then we can easily recover the variance later by computing the exponent of this output. Okay. We need, like, as a concept, the reparameterization trick. So the thing is, we can't backprop directly through basically through the normal distribution here, through the density function. But what we can do is simply rewrite this as the following linear function where we have mu plus sigma. We have used this before, and then I multiply it by epsilon, and epsilon is just my random component that is drawn from the normal distribution. But now mu and sigma are deterministic, and I can backprop through those quantities. So relatively easy. So basically, we have pushed out the randomness out of our posterior. So again, that's very simple to implement. We call a function, we provide the mean and the log variance. You see, like here, the line how we get the standard deviation, and then I compute. Basically, I draw a sample from the standard normal distribution, and I compute Z. Okay, great. The third component we need is like the decoder. So depending on what kind of data you deal with, you have to make some assumption about the distribution. Typically, quite often, I think we deal with like continuous data. So again, we assume for simplicity that P is like follows a normal distribution, which is parameterized by mu and the sigma here. And for simplicity, we set sigma typically to be 1. And if we do that, then this reconstruction term simply reduces to a squared error. So a lot of assumptions for simplifying the problem. This makes the problem easy to train and practice. There are tons of variations. I think there are probably 20,000 papers on this thingy. So you can try to relax the one or other assumption and make it more complicated. But this is like very simple. We have a very simple reconstruction loss. We compute the squared error between our data point and then the reconstructed data point. We typically ignore the constant. So that's all you need for the decoder. With those things together, we can formulate our loss function. Basically, we have formulated the elbow before, but typically, if we train a neural network, we want to minimize something. So we just turn the elbow in a minimization problem. Just kind of take the negative or kind of minimize the negative elbow. And one question is, what are we doing about this KL term? That we have to do. So I show you, this is like the implementation, the mean squared error, no problem. And then for the KL loss, you have like this funny looking thing here. But this comes from the fact, again, we made like all these assumptions. Q is a normal distribution, our prior is a normal distribution. So basically we compute the distance between two normals. So you go on Wikipedia, look for KL diversion, and then you find the derivation. I have a slide here, I will not go over it. And you find the exact derivation there. Or again, ChatGPT gives you a beautiful derivation. And then you come up with this sum here that sums over all the latent dimension, and that's exactly what we implement. Okay. I think I have about 10 minutes, maybe 15. So let's use this, or think a bit about how we use it. Okay, we have this model, we know how to train it. You can look later at the notebook if you haven't done this before, if you like, but generating new samples. So now we can use our two-stage approach. I sample, the model is trained. I've trained the model, and now I just use the decoder. I sample like from the normal distribution, I have my set and I squish it through the decoder and get a generated sample. And again, for the same set, the decoder here is turns out to be deterministic. Okay, I want to quickly look, and that's showing a little bit, I mean, that this can be a little bit tricky, even for a super simple problem. So this is like our simple toy problem. First thing you see, I generated more data. So if you train these models, you need a lot of data. And you can try in the notebook, I have like, even you can compare with the diffusion model. If you ask why we care about VREs at all. If you reduce the data, I mean, the diffusion model will do a good job if you give it enough data, but maybe not so much if you reduce the amount of data. Yeah. Okay. So I want to learn this distribution on the left, given the samples. Okay. So model one, which I carefully tuned. I think this looks relatively decent for in order to, so these are new generated data now. And kind of this matches the true data distribution here. So everything is fine, the implementation seems to be correct. We get something useful. What you see a little bit here is we get a little bit more variance in the dominant eigenvector direction of the covariance matrix. So this is like not critical here, but something that happens, we should keep in mind. And I mean, this is like nice with these simple 1D, 2D examples, you can actually look at this. I mean, you have no clue what happens in high dimensions. But you even see on this simple problem, it's not perfect. Okay. So we can diagnose this behavior a little bit with a simple problem. What I can do is I use my, my posterior distribution, and I encode all my training data points and maps this in the latent space. And I underline my prior distribution. And you see there's a bit more spread along Z1 axis, along one axis, and a little bit less spread along the second direction. But overall, it's not too critical. That seems to be a relatively decent model here. Here's another model. And you see here's even more spread along one direction and gets even more squished. And if you look now to the latent space, you suddenly see there are some holes, right? If I would now go and sample a point from here, that's a point the decoder never has seen. So I don't know I don't even know where this point would get mapped. So something is going wrong in this model here. And this problem can become even more extreme. This is so-called the posterior collapse. Now suddenly, in some sense, the posterior is only considering, or there's only one dominant axis. The other axis is not considered. And basically, it's a one-dimensional problem now, and you see what happens if you generate new samples. So that certainly is not a good approximation for the true data distribution. So you have like a little bit tension here. Where does it come from? I think that's good to see. So think about this KL term as a regularization term, right? So we have this conditional Q, and we have the prior. And it tries to push the conditional towards the prior. But the conditional should not be exactly the prior, right? These are two different creatures. We want that the average over the average behavior over the posterior behaves like the prior distribution. But we don't want that for an individual data point, the posterior behaves like the prior distribution. So that's like a struggle that we have here, though there's some tension. And it depends like how much regularization we have. We see like we have either like drift of the data, what we saw in the first example, where everything was nicely scattered, but things moved away from the origin. And then we had like the other extreme where we had like a collapse. So basically, again, what I say like depends on whether the KL term dominates or not. So there's an approach like this is an extreme here. If really only the KL term dominates, then everything collapses to the origin. So how can we control this problem? How can we handle this? So one very simple approach. Okay, I skipped the slide. This is just what I just said, like this issue between individual and average posterior. What I'm saying, right? We want the average of the posterior to mimic the prior, not kind of the individual posterior to match the prior. So we can use like an additional tuning parameter beta here to control the impact of the KL divergence. So we can either make the KL divergence smaller or larger, and then you get like these different phenomena. And typically you have to do this while you train the model, and it makes like training these models somewhat difficult because like if you here with this two-dimensional data, it's easy to inspect it. But if you have high-dimensional data, you might not even see this behavior, right? I mean, it's hard to know what is going on or if there's a collapse. But yeah, so you can make beta smaller, smaller, so you have a stronger penalty. And typically, you won't have some regularization, right? I mean, you want like a compact latent code. You want that like the latent variables are disentangled. And that would allow you also like, okay, you can compress the data. But on the other side, if it's too strong, you have like this posterior collapse. And if you make your KL weaker, it might improve the reconstruction. But if you make it too small, then the encoder said, I don't care about the latent variable at all. It's just encoding something. And the latent variables are not meaningful anymore at all. So balancing between those two things is work for you as a user of these models. And that's maybe why I would use a diffusion model instead. But anyways, good to have these concepts in mind. Okay, 2 minutes, 3 minutes. Try to be super quick here because we will see all these models in the remainder of this week. But okay, just my view, recap of generative model. We want to learn to approximate the true data distribution. And typically these models that we mainly talk, I guess, this week, I think there's not a single talk about density estimation. That will be always about sampling, generating basically new data, and you can kind of keep this mental picture in. So there are many different models to learn the G1 model. We have just discussed the variational autoencoder. And all these models work a little bit different or use a different starting point to get a G. But in general, we want that our model provides us some high fidelity samples. We want some diversity in the data, right? That for a different Z, I get a different outcome, not just always the same outcome, which I have what would happen if I have mode collapse or posterior collapse. And we hope that our generative model is somewhat fast, because otherwise might be easier to run the actual experiment. So there are these different families of generative models. I mean, there are all kind of different type of taxonomies. So this is one, and certainly it's not complete by any means. But you can think about maybe there are these likelihood-based methods and likelihood-free methods, so implicit methods that do not learn an approximation for the density function. We've discussed the variational autoencoder. There are the interpretation of variational interpretation of diffusion models. You will hear, I don't know if you hear about necessarily this interpretation, but you can think about a diffusion model as a hierarchical variational autoencoder or as a deep variational autoencoder. So we will hear more about this in the next few talks. And kind of for likelihood-free models, we will hear about score-based diffusion models later this afternoon. There will be a talk about GANs on Friday. And then you have like these direct models, so that so on the left, I would say they're like approximate. On the right, they actually learn an explicit density, so-called like, that would be like autoregressive models like ChatGPT and so on. And we will hear a lot about this, those models tomorrow and on Wednesday. Okay. So all these models have different advantages and disadvantages. There is not a single silver bullet. I mentioned this already briefly. It depends how much data you have. It depends on your goal. VREs are nice because they compress your data. You can use them for anomaly detection. You can look to this latent space. Diffusion models don't allow you to do that. They operate in ambient dimensions, but typically they're, in my experience, a bit easier to train. More expensive, but like not as brittle. Typically, the generation process of a diffusion model is more expensive. So if you don't have fast GPUs, then you only can do a VRE. So it depends a bit on your resources. GANs, they're known to provide really good, high quality samples, but they're like super tricky to train. I mean, there are like, I think, a lot of variants which largely have solved this problem. But in general, diffusion models produce the same quality and have some additional advantages. So I would stick probably to diffusion model over a GAN, but nevertheless, there are some nice applications about GANs. And then you have like autoregressive models, or particular autoregressive transformers. They're good for different problems maybe as well. So it depends, like if you want to do time series forecasting, or if sequential data, or if you just have image-like data. So you need to know about different models and then pick the right model for your application. So I skip over this, that you can just look this like just a nutshell summary of some models. So let me go over that. And I probably should end here. Okay, just my conclusion. Well, so I think like these generative model, I hope I conveyed this concept a little bit. They're great to understand data, not just modeling data in a sense like discriminating between two classes or do just regression, but learn something about the underlying data distribution. So you typically should learn better representation, and these representation might be useful for downstream applications as well. You typically need more data to train these models. So that's a challenge. If you don't have data, then it's hard to use generative models. I think there's a lot of success stories already of generative models in science and for climate, for materials, for proteins. And I guess we will see many more successes in the future. Still, I think we are relatively early in the sciences to use these models, probably a few years behind computer vision, behind NLP. So lots to do. So yeah, I believe these models will accelerate scientific discovery, and I end here. I guess we have a break now, so I will just stand here if you have questions.
Stand here. There should be, there's probably some food left outside. Again, once they stand outside, how hard for all of this door as well. Back there, start getting left.
Hey. Hi.
Yeah.
Yeah.
I wonder if so on,
Well, so standard, so there should be something stochastic, right? The standard autoencoder is completely deterministic. So you don't sample from a base distribution. It doesn't have to, right? So basically, for the same input or for the same layer, it always gives you exactly the same answer. So that's not what happens with the variation. And yeah, so the definition here that I have is loose, but you can formalize it by doing everything to a push forward metric, if you like. I mean, I'm simplifying, right? I mean, if you think about probability, you can be formal and start with a set theoretic approach about it and build everything from there. In our problems, typically everything is nice with what was in the data. So loose formulation works first.
Yeah, maybe like I'm wondering that how autoregressive models might also be called GenAI.
No, they're not. They're not, right? I mean, they learn a probability distribution over the tokens, over the outputs, right? So it's like, and then they pick one token, but not always the token was. I mean, you could set them to you can make them deterministic, like a transformer can be deterministic, right? But like language model GPT, computing a probability distribution and sampling a token, and it does not always sample. So you can try this simply by entering the same prompt twice in two different windows, and you will get two different answers. Because you might sample a different word, and then you run over the same sequence again and again, but every time you pick like a different, potentially a different next token, which makes it generative. Just a different approach, like just a different factorization, right? So they use like so you cannot use directly the data distribution. You typically have to factorize in some way and make kind of start with a simpler problem and build up from there. And then autoregressive process is one form of factorization. Here we introduce the latent variable, which is another form to do stuff with. Yeah, no problem. Which is slightly different from the possibility. So most of that arises from the decoder. So basically, the encoder is able to do it. And that way, the encoder has no interest in creating high fidelity data or worse data. So that's different from theoretical